Two main things have happened over the last 20 years. So computers have got much faster. As you get more compute, you can include more details. If you include more details, then you're going to be closer to the reality. And then remote sensing. The amount of information that we have generated over the last 20 years from both NASA and other agencies and satellites has been incredible. We have the series measurements tracking the energy fluxes at the top of the atmosphere. We have MODIS, which has been tracking cloud changes. It's really been a golden age for Earth observations over the last 20 years. And that's radically changed how we understand what's happening and how confident we are that our predictions are skillful and relevant.
You're listening to A Climate Change. This is Matt Mattern, your host. I've got Gavin Schmidt on the program. Gavin's a noted climatologist, climate modeler, director of the NASA Goddard Institute for Space Studies in New York. One of the things, he took over that post from Dr. James Hansen in around 2014, and everybody knows James Hansen, who famously warned Congress about global warming back in the 80s. So you stepped in some big shoes to fill and are filling them quite well. So kudos to Dr. Schmidt. And, just to give you a little background on, his education, Oxford, PhD at the University of College of London in applied math, postdoc at McGill, which my dad went there for a little chemistry master's degree eons ago. Author of 100 studies in peer-reviewed journals, Science and Nature, co-authored a book, Climate Change, Picturing the Science, with a foreword by Jeffrey Sachs. And welcome to the program, Gavin.
Well, thank you for having me.
Well, tell us a little bit about the work that you're doing over at the NASA Goddard Institute in New York, because I didn't even realize that there was a NASA program in New York. So
Oh, well, news to many people, in fact. We're not a very large part of NASA. We don't launch rockets from the roof or anything, but we've been at the forefront of climate modeling, understanding why things are changing, how things are changing, how they're going to change in the future for many decades now. One of the main things that we do, which is not everything that we do, one of the main things we do is build and develop climate models. These are the kinds of models that go into the IPCC reports that are being used to project, what might be happening in the future, to allow us to prepare, to allow us to mitigate those changes. And we've been working on this kind of modeling, like as you mentioned, since the 1980s, way before I got there. And so I've kind of inherited this program, and we've taken it forward. But the idea is that you really want to capture the essential processes of what happens in the climate system, and then the essential changes and how those changes work their way through the system. Things like changes in the emissions of aerosols from marine shipping, changes in the sun's radiation on a solar cycle timescale, impacts of big volcanic eruptions, the changes, of course, to atmospheric composition, greenhouse gases, carbon dioxide, methane, and the rest of it. And then see what the fingerprints of those changes are, so that then you can look in the observations and say, hey, are we seeing what we expect to be seeing? What do we? How well are we doing that? How skillful is that? And therefore, how confidently we can predict? Can we predict what's going to happen in the future?
Well, tell us a little bit about, for us space tech geeks out there, what kind of tools do you have floating up in the atmosphere and maybe in the ocean and all over the place that are giving you the measurements that you're relying upon in doing this modeling?
Right. So the kind of modeling we're doing is a little bit different from weather forecasting, right? So weather forecasts use the same basic kind of structure of models, and they ingest all the information they can find, for today, so that they can make a better prediction for tomorrow, next week, etc. We don't use data in quite the same way. We use data observations to try and pin down what the essential processes are, how clouds form, how much evaporation changes if the temperature changes or the humidity changes. We try and extract out those processes, how reflective sea ice is when it's wet or when it's dry or when there's been new snow that's fallen on top of it. We encapsulate those things into parameterizations, formulas, code, and then we try and see how that whole system works. And then the other kinds of observations that we're comparing against are the observations of big emergent properties of the system, how the clouds change when you have an El Nino event or a La Nina event, how the trends of clouds are changing. Those are made up of many different processes all happening at once, and we're trying to see with these models whether we can capture that emergent property of the observations in the emergent properties of these models, and then make a link between those things. So we use remote sense data from NASA and from other agencies. We use in situ data. We use special kind of campaigns that are very targeted on, there was a mosaic exhibition in the Arctic looking at the physics of sea ice and the oceans and the atmosphere above it. We take information from these field campaigns, from the remote sensing, from in situ observations from the buoys, and then use all of it as much as we can to both improve the model and then to evaluate the changes that we're seeing over time.
And in terms of since you started doing this to where we're at today, what kind of improvements in the science have you seen that have made you believe that it's more reliable or less reliable?
No, it's more reliable, which is good, right? No, it's more reliable. Two main things have happened over the last 20 years. So computers have got much faster. That is by far the biggest thing, because as you get more compute, you can include more details. If you include more details, then you're going to be closer to the reality, and that helps a lot. And then remote sensing, the amount of information that we have generated over the last 20 years from both NASA and other agencies' satellites has been incredible. We have the series measurements tracking the energy fluxes at the top of the atmosphere. We have MODIS, which has been tracking cloud changes. We have MLS that's been looking at water vapor changes in the stratosphere. We have the GRACE missions that have been tracking the loss of ice from the ice sheets. All of those things are going into the mix, and it's really been a golden age for Earth observations over the last 20 years, and that's radically changed how we understand what's happening, and how confident we are that our predictions are skillful and relevant.
And in terms of those predictions, have they changed markedly since you started doing the modeling? Meaning, does it look worse for us or better for us than, 20 years ago?
So, I mean, the interesting thing is that if you go back even to the 1970s and you ask people at the global scale, what do you predict as we're increasing the amount of carbon dioxide in the atmosphere? And I even going back to the 1970s, those predictions were very skillful. In the 1980s, they got more complicated, but didn't really change in the global mean picture, and that has been constant. So in some sense, we're predicting the same things that we were predicting, 40, 50 years ago. And they have, in fact, by and large, been borne out. But we're now able to predict a lot more things, right? We're now able to predict things like the changes in extremes of rainfall intensity, the changes in the statistics of heat waves, the changes in the sea ice, the changes in the Southern Ocean. And that's come about because we've increased the complexity of these models, and we've been able to verify how well they do against a much deeper bench of climate statistics than just the global mean temperature, which, as I mentioned before, has been well predicted for many, many years. But we're doing a much better job now at predicting the far field effects of an El Nino event, or changes in the El Nino events, or what happens to storm tracks, what happens to the intensity of storms. All of those things are now kind of within the scope of the models in ways they really weren't 30 or 40 years ago.
So, in terms of working on the variability of ocean circulation, which you've done a lot of work on, what are those models telling us? And should we be extremely worried based upon what you're seeing?
Well, yes. The basic issue, I mean, as you're well aware, is as you increase the amount of greenhouse gases in the atmosphere, that slows down the emission of energy to space, which means that there's an energy imbalance. There's more energy coming into the system than is leaving. Most of that energy is ending up in the ocean, where it leads to marine heat waves, sea level rise, melting of the sea ice, melting of the Antarctic ice shelves, which all add to sea level again. The warmer oceans are fuel for storms, particularly in the tropics. The intensity of storms has increased. The intensity of rainfall associated with these storms, not just tropical cyclones, but frontal systems everywhere, that's increasing, and so we're seeing increased intense rainfall pretty much everywhere. And all of these things are consistent with our understanding of what has been driving this and what has been happening in at the local scale. The big difference from 30 years ago is, I think, that the signals really had only kind of started to emerge at the global mean, the global average level, where they were quite clear, from the 1980s onwards. But nobody lives in the global average, right? Like everybody lives in a very local, regional kind of environment. And for a long time, people like myself were saying, well, global warming is happening, but everyone's saying, well, it's global warming like everywhere else. It's just so much noise. So what's happened now, and particularly in the last 5 years, is that the signal in the global mean has become so large, right, that it's extremely clear. But it's so large, it's large enough now that it's having a reflection in the weather and the impacts at a very, very local level, right? And so climate change used to be something a little academic, a little esoteric. That's no longer the case. Climate change is having real impacts every day. And we're seeing that in the analyses of the rainfall from Helene. We're seeing that in the analyses of the LA wildfires. We're seeing that in the analyses of the Pacific Northwest heat wave. We're seeing that in the analyses of the sea level rise and increased storm surges that we're seeing in Miami and in Newport and in, all up and down the West Coast, the East Coast. So.
So, one of the things that your bio talks about is astrobiology, and maybe you can explain for everybody how that fits into the work that you're doing.
So that's kind of interesting. So astrobiology is really the study or the thinking about what we might be able to detect, what we might be able to see in extraterrestrial environments that might be related to life elsewhere. And obviously that has been one of the main drivers of our desire to explore the universe. Are we alone, right? What else is going on? And we have this fundamental not an understanding, a wish for us not to be alone, for us to be able to find other civilizations, other forms of life in the universe. But to do that, there's a lot of stages that you have to go through. We have to we have to explore the other planets in the solar system. We have to detect other planets around other stars. We have to characterize what's going on those planets. What kind of climates do you have if you're in a tidally locked orbit around a red giant? That's a very different kind of cosmic circumstance than the Earth. But it turns out you can still have a habitable zone. You can still have situations where you could have liquid water on the surface of the planet. And given that we're looking for the most part for life that somewhat resembles ours, right? Liquid water is one of the key ingredients to having that be there. And so understanding the climate of exoplanets is not that different conceptually than understanding the climate of the Earth. And so there's a very clear link between the models that we develop for the Earth that have been informed by so much information that we can then use those models to explore the climates of other planets or other exoplanets and say, which one should we concentrate on that might be the most Earth-like, that might be the most convivial to life. And then we have this kind of concept of searching for what are called technosignatures, right? Can you detect the impact or the entrails or the fingerprints of other technological civilizations, right? That we might conceivably be able to communicate with. What kind of fingerprints do they leave in the kinds of things that we could observe either from space telescopes or in the sediments of Mars or conceivably even the sediments of Venus? What would we look for? One of the things that we worked on, which is kind of amusing, is what are the fingerprints that we're leaving behind, right? So we've heard about the radio wave that has emanated from Earth that would in fact be detectable from nearby solar systems. But what about other things that we're leaving behind? People think about relics, but we've been thinking much more about the geophysics, right? So what are we leaving behind in the ocean sediments? What are we leaving behind in the kinds of things that we look for when we go back in time over the Earth? We are leaving behind a massive perturbation in the carbon cycle that's very, very clear in the isotopic signature of the carbon that we're putting out. Where we created global warming, that's going to be very clear in the ocean sediment. We're creating a layer of plastic debris that will literally cover the entire ocean floor in a thin and but very clear and distinct plastic layer. We're changing the amount of minerals and metals that we're mining, and that's all ending up in the ocean as well. The amount of gold that we're putting into the ocean because of the mining of gold and then the use of gold within electronics and manufacturing has increased the amount of gold that's going into the ocean by orders of magnitude. All of these things will be visible in the future. So if you think about a future paleoclimatologist of some visiting species coming to Earth, they will be able to see, even if we don't do anything more than what we've already done, they will see our fingerprint. They will see our signature.
And they might wonder, why the heck were they using so much plastic? Why were they emitting so much CO2?
I think that they will be quite puzzled, yes.
Like when they had alternate materials, they clearly had it within their reach to have cleaner energy and have a cleaner environment, yet they chose to live this.
There's a very interesting kind of consequence of what you just said. Almost all of our detectable fingerprints are in some sense a waste, right? Sending radio waves into space is a waste of energy, right? We're not doing it to do that, right? Filling the oceans with our garbage is a waste. It's resources that we're just throwing away. Carbon dioxide is a waste product from the burning of fossil fuels. All of the things that we can detect, they're accidental. They're signatures of our unsustainability. If we were to become a society that was much more sustainable, then our fingerprint on the environment, on the earth, on the cosmos would become much smaller. And one of the interesting kind of solutions to the Fermi paradox, do you know what that is?
I do not.
So the Fermi paradox is, if you think that the universe is very old, which it is, and if you think that there are millions upon millions of exoplanets, which there are, and then you think that, well, life can't be that difficult to create, right? Then the paradox is, why have we not already seen evidence of alien civilizations or alien life? If the galaxy is billions of years old, that's a very, very long time. Surely somebody would have come by, somebody would have left something. But we've not detected anything. And so Enrico Fermi said, well, what? That seems a puzzle. What's the cause of that puzzle? And there's been a number of theorized reasons why we haven't detected anybody else. One is we are simply alone. We are unique, but nobody really likes that answer. Another one is, life pops up, civilizations pop up, but there's a great filter. There's something that prevents civilizations and life from becoming, a galaxy-wide phenomena. The difficulties of faster than light travel, so you can get away with that with robotics. Perhaps nuclear power or nuclear weapons or energy like pollution. Maybe everybody pops up and then they just kill themselves because they pollute their own environment to such a degree that they can never really sustain it. And then there's another one which philosophically I prefer, is that for a civilization to be really, really long-lived, right? Not a few hundred years that we've had here, but really long-lived, million-year civilizations. You cannot possibly have an unsustainable civilization. You have to recycle everything. And the reason why we haven't detected any of these civilizations is because they leave no trace. And so that's the kind of the sustainability solution to Fermi's paradox. And that kind of comes into, what does the Anthropocene look like, right? Because everything that we're doing in the Anthropocene is predicated on absolutely huge amounts of waste that's affecting the ecosystems, waste that's affecting the oceans, waste that's affecting the atmosphere, or even our kind of near Earth environment. All of those things. If we have ambitions to be a million-year long civilization, none of those things can be sustained for very long at all.
We're heading for a quite shorter run based upon the trajectory that we're on. So tell us a little bit about coming back to Earth a little bit. Tell us a little bit about the Arctic, and certainly we all are reading more and more about how fast the climate is changing in the Arctic, and it's much faster than it is in the temperate zones that most of us live in.
Well, that's exactly right. So this was one of the things that was predicted very, very early on, that the land would warm faster than the oceans, the northern hemisphere would warm faster than the southern hemisphere, and the Arctic would warm fastest of all. And as the data has come in, those predictions have been well validated, and we are indeed seeing temperatures in the Arctic warming at about 3.5 times as fast as the global mean. Right. So this last year, we probably exceeded 1.5 degrees Celsius above the pre-industrial for the first time in a single year. But in the Arctic, the warming has been 3 times that, right? So it's like 4.5, 5 degrees Celsius. So that's like 7, 8 degrees Fahrenheit. That's a huge, huge shift in what happens there. Obviously the Arctic, oh well, it's cold. It's not quite as cold as it was, but like at the margins, what you see is, in the spring, the ice goes away faster. In the autumn, it doesn't arrive so early. The season for ice roads in Alaska has shrunk by about 100 days over the last 30 or 40 years. Right? I mean, that's a huge shift in how you get around, what you do, how you live, how you hunt for the indigenous folks there. That has knock-on effects, even in the temperate zones. Melting of the ice in Greenland raises sea level everywhere. And so we can see it, particularly along the east coast. We're seeing the fingerprints of the warming Arctic in sea level rise, in emissions of carbon and methane from permafrost melting regions. We're seeing it in ecosystems. We're seeing it in the biosphere there.
Well, you've written about the methane imperative and the need for us to cut our methane emissions. Um, tell us why that's so important, and what are we doing, and how can that be speeded up, if at all?
Right. I mean, so the dominant greenhouse gas that we've changed is carbon dioxide. Uh, but then the second most important one is methane. And methane has both direct effects, so it's a greenhouse gas in and of itself, but it also changes the chemistry of the atmosphere, and it produces bad ozone, right? So ozone in the lower atmosphere, which is toxic, and you don't want any of that in the lower atmosphere. You want ozone in the stratosphere because that's where the ozone layer is. But this is different. This is much more of a greenhouse effect, and so methane changes affect both criteria pollutants like ozone and smog, but also they have a direct effect on the climate as well. And so if you add up how much temperature change the methane has caused over this period, it's about half a degree Celsius, right? So that's about a third of the temperature changes that we've seen. Can be attributed to methane. So if the methane levels that we have more than doubled since the pre-industrial, right? So since the 19th century, it was around 700, 800 parts per billion, and now it's close to 2,000 parts per billion, right? So that's a huge increase. It's driven by a number of different things. So oil, gas, coal, infrastructure, mining, leaks, all of those things contribute quite a lot. Landfill is a big contributor because you have kind of anaerobic stuff that's happening in the landfills, and if that's allowed to get into the atmosphere, then that adds to the methane in the atmosphere. And then you have agriculture. So agricultural emissions of methane are mostly due to large herbivores, particularly cows and sheep, which have a kind of fermentation that goes on in their stomach that gets them to produce a lot of methane, mostly burps. So cow burps and sheep burps are a big deal. And you think, wow, it's just a cow, it's just a sheep. But it turns out that we have increased the amount of biomass in cows and sheep by huge orders of magnitude compared to the pre-industrial levels of ungulates and things like bison and stuff like that. We have far more sheep and cows than we ever had bison, for instance, and that's enough to shift the balance in methane in the atmosphere. So anything that you can do to reduce methane by reducing leaks in fossil fuel infrastructure, by adjusting the diet of animals too, so that they produce less methane, all of those things, by capping landfills and using the methane that's coming off landfills as biogas to power homes and industry. All of those things are very helpful to bringing down the level of methane. And because methane doesn't last in the atmosphere as long as carbon dioxide, it means that action now on methane can have an effect that's much quicker than reducing carbon dioxide emissions. But obviously, you have to do that as well. So these things should not be played off against each other. But they are both ways in which we can minimize climate changes in the future.
I've read recently about I think it's nitrous dioxide that has is even more powerful than methane as far as a
Right,
su-
but it turns out that's only increased by about 15% since the pre-industrial. So that is an issue. But it's in terms of what its contribution has been to the global warming so far, it's much smaller.
oh, okay. Well, one of the things that I've read about you is that you were involved in the attribution science, or the science of attribution, and I think that's going to become a big thing in the coming years because, as a trial lawyer, I'm thinking damages, I'm thinking causation, I'm thinking that polluters are going to be called to account in courts of law eventually.
Yes, yes. There was a very interesting workshop at Columbia that we're right close to that looked at that in quite some detail. So this was effectively lawyer led, right? And these are folks who've been involved in ongoing lawsuits, some not successful, some successful, and some still in play, related to exactly that issue. To what extent can you demonstrate that actions of polluters are causing recognizable harm, and finding people withstanding to make those claims? And there's a lot. There's a lot of very deep legal thinking that's going into this. And they are kind of working, like I guess it's a kind of a co-production, working with a lot of climate scientists to be able to make the causal links that are required in such a lawsuit. And there's been some very interesting work recently. One thing that's kind of interesting is work that is being done to attribute climate changes, not to the kinds of things that we have traditionally done, which is like attribute it to carbon dioxide, to aerosols, to methane, to land use change, but to companies, and particularly the scope 3 emissions of the large fossil fuel companies. And if you start to say, okay, well, how much carbon dioxide has been put into the atmosphere because of the actions of Saudi Aramco, Chevron, BP, ExxonMobil. And then you say, okay, well, that's your contribution to the carbon dioxide changes. Here are the climate damages that are associated with those things. And then here's the link here's that causal chain between your scope 3 emissions, the changes in the climate, the damages, and here's the person that's been damaged. And like kind of tying all of those different steps together with as thorough a science as you can do, it's getting very close to being able to say, company X, you are responsible for Y trillion dollars of damage, of which some portion of it is this person here who's suing you. You have to pay your share, and it's it's a very impressive development of that kind of legal edifice that I think is that's not going away.
Yeah, I think that it's certainly part of the piece of the puzzle because, quite frankly, why we're in this situation is because fossil fuel companies and society at large had not valued the cost of pollution. And so this is essentially rectifying that by saying, "Hey, there was a cost to pollution. You knew what the cost was, Exxon. You studied it in the '80s. You knew that these effects were going to come. You had your own, you predicted it accurately. Your science was good. You knew the disaster was afoot, and you proceeded ahead, without any regard for the consequences. Our society has, for hundreds of years, said the person who does that is responsible for the damages.
Right. So, I mean, the interesting thing is that you can still be responsible for damages even if you did it inadvertently, right? There are other issues, I think, with legal efforts to hold the oil companies to account for the climate misinformation and disinformation that they put into the system over the years. But I think that's somewhat separate to the attribution of their actions to real damages, because it doesn't really matter why they did it or whether they were knowledgeable about it. They're still responsible.
That is a very good point. I think I'm going to put you on the legal team. You know, some of the work that you've done regarding ocean warming, you've written about acidification, and that the combination of that relation causation from bottom trawling of the fishing industry. Tell us a little bit about your study on that front.
Yeah, I mean, this is the big picture on climate change and what's causing, the big changes. Is pretty well done, and so we're doing a lot of work. Kind of, I mean, I would not marginal, but we're doing work on the smaller terms, right? We know where most of the carbon dioxide is coming from, and but we like kind of as the models become more complete, as we start to think about different things going on, we can get to the smaller terms. And so one of the things that we were looking at recently was the impact of bottom trawling, which is not great even in its own context, right? You're looking at the continental shelf. You're kind of like grabbing everything that is literally sitting on the bottom. You get a lot of bottom feeding fish, which is the point, but you also destroy a huge amounts of habitat for things that you don't really care about. So there's a very large bycatch associated with that, and you end up with very very large, effectively biological deserts at the bottom of the ocean. But one of the aspects of that is that you're also taking that sediment and you're taking it, and a lot of it is very it's fish poop, right? That's fallen down, algae, plankton, very high in organic matter, and is settling down, and then it kind of decays on the bottom. But you're taking all that, and you're throwing it back up into the column, where it decays in the column, and then it adds back carbon dioxide into the ocean, and then that feeds back into the carbon dioxide at the surface, and then that leads to outgassing. And so by doing a lot of bottom trawling, you're actually it's a small source, but you're adding more carbon dioxide into the atmosphere. Again, so if you needed more reasons to think that bottom trawling was not a good thing to be doing, then this is like one extra little bit that says, oh, it's also impacting the climate.
Yeah, it's pretty tragic, the things that are going on in the ocean in terms of overfishing, and now they're talking about mining, which sounds like a disaster in the making. Well, tell us a little bit about what are the things that you are working on right now that you think are particularly valuable in this whole conversation.
Sure. I mean, talk about a couple of things. One is we know that the ice sheets are losing mass. Right, we have direct measurements of the gravity of these ice sheets that say that the mass in the ice sheets is going down. What does that mean? That means that the ice that was in the ice sheet is now in the ocean, and that's a large enough amount of water to start affecting ocean circulation, to start affecting sea ice, to start affecting stratification, currents. And so we're working on a project to try and upgrade everybody's estimates of those impacts, so that we can capture that when we're doing kind of our historical simulations for what has happened, and then do that better attribution, and then for our projections into the future, so that we can include the increases in melt from Greenland, for instance, perhaps impacting the North Atlantic. So that's like a kind of a process-based thing that we're doing. But perhaps kind of more interesting to your listeners is we're working a lot with machine learning. And we're looking at machine learning to try and improve the climate models, to calibrate them better to the observations, because it turns out that with these models, you have a lot of parameters that you don't really know what number you should pick. You have some range, but you don't know what number to pick, and you don't know how they interact with all the other different numbers, and that's a very very large problem. It's a very big data problem. Tens to hundreds of degrees of freedom. That's a massive phase space to be looking for. And we're using machine learning to kind of short circuit that and find the best calibrated models that we can in ways that we never would have been able to do. Manually, just by kind of like tweaking parameters to see what happens. So that's extremely useful, and that's allowing us through a kind of a process of emulation of the models to expand the number of models, the uncertainty in the models, like quantify the uncertainty in these models, and then make better predictions going forward. Again, using emulators to explore a much broader range of scenarios than we've been able to do so far.
So that's essentially AI that you're using to
Yeah,
improve.
and it's not ChatGPT or any of these large language models that spend their time hallucinating. Work that people email me. Oh, I loved your paper from 2017 on blah 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 blah, and I'm going, I never wrote that paper. It's the kind of thing that I might have done, but I didn't. And then you kind of say, yes, thank you for your comment. Where did this reference come from? Oh, ChatGPT told me all about it. It's like, yeah. Anyway, so you don't want to be using that for anything scientific. But the techniques of machine learning in dealing with very, very large data sets, extracting out the patterns, and then kind of encapsulating that in a very efficient way, those are real gains, and they allow us to do things that we were never really able to do before we had that technology. So there are real gains to be made from machine learning applied to the climate problem, but it isn't asking ChatGPT what the temperature is going to be like in July 2025 or something.
Well, that's fascinating. Well, I really appreciate having you on the show, and in particular, one of the things that popped out to me was your view on sustainability of looking back. If a culture looks back at us and says, hey, what would they see? And then also, if we want to be that culture that survives, we're going to have to be sustainable. And I think that that's kind of a good message to put out there. Hey, if we want to have that for ourselves and our future, we have to go in that direction. Disaster is the other alternative.
And there's no real choice, right? We talk about sustainability, but we don't really talk about sustainability with a kind of cosmic time horizon. And I think we should, going back to things that Carl Sagan or Neil deGrasse Tyson have said. We're just like one little pale blue dot, like kind of floating in the cosmos, and our problems don't really amount to a hill of beans compared to everything else that's going on. But if we want to persist, we have to think in that very, very long term way, because that tells us how we will persist. It isn't the way that we're carrying on now.
Right. The indigenous societies, I guess, talked about 7 generations out. I don't know if we're going to make it 7 generations out, given our current thinking, but we've certainly got to alter it further and further out. So we're taking a longer view of what the future looks like. And I drive a hydrogen car, and Toyota has a 100-year plan for rolling out hydrogen. And that's kind of mind-blowing in our corporate world to think 100 years out, but that's really short-term thinking. That's myopic. 100 years is myopic.
Yeah, I mean, one of the advantages of working for NASA is that it's totally within scope to think about scales the size of the galaxy and time scales the length of the life of the universe, but also at the same time thinking about processes in clouds that happen on the micrometer, millisecond timescale, and all of those things from microseconds to millions, billions of years are kind of like within our scope to think about, to explore, and to learn from. And I've been enormously lucky to have been in this position. Hopefully, we can continue to do that.
Thank you so much for being on the show. We appreciate all the great work that you're doing and the great thinking that is going on at NASA. I think it is the future, and we need to start thinking that way thousands of years out, millions of years out, because it's a whole different type of care that we will take with our planet if we are actually thinking like that.
Yes, indeed. Thank you so much for allowing me to talk about it.
To learn more about our work at A Climate Change and how you can help us reach our goal of planting 30,000 trees in the Amazon this year, visit aclimatechange.com. Don't forget to subscribe to our podcast on Apple, Spotify, YouTube, or wherever you get your podcasts. If you like this episode, please share it with a friend. See you next time.